Hi guys, Nish here. My presentation topic is volume by slices. So I want to start with why do we need this topic? Why do we need this application? So we have already went through dimensions, right? Where we got to know how can we find the area? How can we find the area of this 2D shape or any 2D shapes, right? Or area under any curve. So what we were doing there was very easy. What was that was pretty easy. We were just cut this area into infinite many thin rectangles, and we were just taking the sum of all those rectangles area, and we were actually getting the area under this curve. So in short, we were just taking the integrals and we were getting the area, right? It was so easy. But what if we would have a 3D object here? What if we would have a 3D cube here? How would you determine the size of that 3D object? How would you find the volume of that 3D object here? Here my topic comes in, volume by slices. Alright, so how can we find the volume of any 3D object by using my topic? Alright, let's say we have a 3D object like this. So what we are gonna do is we are gonna just cut this into infinite many very thin slices. Let's say these are the infinite many slices like this. And the thickness is very small here because it's an infinite slices, right? Alright. And if you take this one slice ahead, and this slice is called cross section in a mathematical way, and I will tell you why it's called cross sections. Let's take this as a cross section now. So each cross section has a radius r, right? Because ultimately it's a round, it's a circle, right? So it would have a radius r, and its width is very small, so we would take delta as a width. So it's a delta width, and the radius is r, right? So what would be the volume of this round? What would be the volume? So the volume is always gonna be area into height, or but in case we would have a width here. So area into width, right? This is gonna be the volume of one single slice, right? But our area is pi r square, right? It's a round, of course. It's a circle, pi r square. Pi r square, and our width is delta here. But this is for only one slice, right? We have a multiple. In fact, we have an infinite many slices, cross sections. So what we will do is we would take sum of all these infinite many slices, right? So for now, this is our general formula for now. All right, so volume, it's area into width. So area is pi r square in case of a round or a circle. All right, pi r square, and our width is very small, so we would take it as a just delta width, and we will sum up all this infinite many slices into ones. So our volume of all this 3D object is this for now. All right, now let's move on to the real textbook type examples. You won't be given the shape of any 3D object here. You will be given a graph. So how would you convert a graph into a 3D object? I will show you how. So we will be given a function like this, root x, right? And we will be given a range from 1 to 4. So we all know the graph of root x, right? It's like this. So how would you imagine a 3D solid from a graph? So what we will do is we will just revolve this, we would just rotate this curve around the x-axis, so we would get a solid. So you can imagine it like this. You can imagine the solid like this. It's not perfect, but just take it for now. Alright, so what we will do is we will just cut this into infinite many slices, and each slice will give us the formula of this, right? This was our general formula from the past iteration, right? V is equals to limit n tends to infinite sigma I is equals to 1 to n, the sum of all slices, right? And what was the volume of each slice? The area into width, right? So let's say we are just keeping the area as a of x right now, right? Into delta x. So why a of x? Why just not a? Because the area of each slice is going to be different, right? Because this slice is smaller than this slice, so the area of this slice is going to be, obviously it's going to be smaller than this, because because our radius here is f of x and our width here is delta x. So our radius f of x is going to be different for each slice. Our radius is bigger here, so the area would be obviously bigger, right? That's why our area is changing according to the x. So our variable is going to be x, right? All right, but it's not going to be a of x as well. What it's going to be? It's going to be xi of star. So why is this? Because even our a is not fixed. Here we took pi r square as a area because we had a cross section of circle shape, but the cross section shape would be anything different, right? It could be one square. What would it be if we had a square, right? The area would be different, and we would see a lot of like this flask shaped cross sections as well. In this type of question, we would do is just nothing but a is equals to like the f of x minus g of x, like this, like the outer minus inner functions area. So we would get the area between these two, right? So the cross section in these types are different. So all of the shapes cross sections are going to be different. The area of all of the cross sections are going to be different. So we would take a of x as a of xi star. Okay. So all right. Does it look familiar? Let me remind you. What was that? The formula for Riemann sums, right? We derived this and we got a to b f of x dx. We got this from this, right? So similarly, we can write this in this form as well, because ultimately this is also a Riemann sum type, right? This is identical to the Riemann sum. So we can write this in a integration as well. So what is our range here? Our range is 1 to 4, but as a general formula, we will take it as a to b, right? Our range is from a to b, and our f of x, we had a f of t here, so we took it as a f of t here, but we got a of x here, so a of x dx. This is gonna be our formula. Alright, so let's solve the end-to-end problem from our textbook. So this is the question from the textbook. Use the slicing method, volume by slices, to find the volume of the solid of revolution. So what is the solid of revolution? The solid of revolution is nothing but the graph we rotate from the x-axis, and the solid we got is the solid of revolution. So bounded by the graph of this, f of x is equal to x squared minus 4x plus 5. So this is our function here. From x is equals to 1 to 4, from 1 to 4, and rotate at x-axis. Alright, so this is our graph of this function x squared minus 4x plus 5. So what we will do first is we will imagine the solid of revolution. So our solid of revolution is gonna be it's roughly gonna be something like this. Alright, so we would do nothing but you don't need to do this, but if you would do, it's better to understand, right? Alright, so we would apply our main formula here. V is equals to, our volume is gonna be from a to b, a of x dx. Our area, the integration of our area from a to b, right? The integration of our area from a to b of each slice. Alright, so what is the cross section here in our case? Of course, around circle here again, right? So this is gonna be the easiest problem here for us because our cross section is circle. So pi r square, right? And r is gonna be f of x in our case. F of x whole square into dx. As our pi is constant, we would take it as outsider. Alright. Our f of x. Our f of x is nothing but this. X square minus 4x plus 5 whole square into dx. You can easily solve this problem, right? You can easily solve from here. So we have a multiple trick to solve the whole square of 3 terms, right? But I would just write the answer real quick, right? Alright, so this is our answer from squaring this all out, right? And I forgot to change the a and b range. What is our a and b range in this case? 1 to 4, right? X is equals to 1 to 4. 1 to 4, 1 to 4. Alright, so we'll do integration of this. It will give us x raised to 5 by 5 minus 8 to x raised to 4 by 4 plus 26 into x to cube by 3 minus 40 into x square by 2 plus 20 x. Alright. This is from 1 to 4. And if we would find the last answer, it's gonna be 78 pi by 3 unit cube. So this is our volume. Alright, so this is how we can find the volume of any 3D object or any 3D solid created by a function or a curve of a function. Alright, I hope this video would be clear to you. Thank you.